talk, but I remember the incredible excitement of the moon landings. And my recollection, this is the most publicized astronomical event since Neil landed. Maybe people would disagree, but it's just amazing the press coverage that is already there, and we have another few weeks to go. So there. So when may I start? Everything's okay? How ancients predicted eclipses, and I made a mistake in the title, but I'll get to that in a little later. Early religions, you had priests, shamans, astrologers, whatever you call them, that came up with supernatural explanations for how life existed, and also giving them an easier life than working in fields for 14 hours. And often the supernatural beings were astronomical objects like the sun or the moon. Can you imagine the effect of an eclipse? If the sun turned dark, disappeared over a land, would that mean that the gods are angry with the king? I have a couple of things to mention. A king in the Emperor of China, his astrologers did not predict the eclipse, and he executed them, not doing a good job. I read about a man that visited Yucatan and was staying with a family that were of Mayan descent. And they'd probably been Christian for maybe 30 generations since the Spanish invaded. And the lady, the mother, was a science teacher, went to university, took all the courses, and during a lunar, not a solar, but a lunar eclipse, she was in rank terror. These are really serious events. Okay, I'm going to bounce back and forth between history and modern interpretations. This is the orbit of the moon, and on August 21st, the moon is going to be very close to Regulus. As the Earth goes around the sun, around September 17th, not this diagram, but a little further, the moon is also pointing to Regulus. So the period compared to the stars is 27.3 days, but it takes another 2 days for the Earth to go far enough that the moon is new again. Now, the key to understanding eclipses is the tilt of the orbit. And it's tilted by 5 degrees. And in my diagram, this is trying to show the part of the moon that is below from the northern perspective, the ecliptic or the plane of the sun. And this is the part where it's above. And if it turns out that there's a certain spot where the moon crosses the ecliptic, and this is what's called the line of nodes because it's crossing the ecliptic here and here. So eclipses only occur when the new and full moons are close to the nodes. And 3 lunar cycles later, you've now got a situation where when you have a new moon that's close to the sun, it's well below, i.e. south of the sun, and that's a new moon, and the full moon is way above, so you don't get any eclipses here. But 6 lunar cycles later, you get now a case where the line of nodes roughly points towards the sun, and you have eclipse season again, and for every eclipse season you have at least 1 lunar and 1 solar eclipse somewhere, and sometimes 2. Now, 12 lunar cycles is going to be 354 days, so the new moon comes a little earlier in our calendar every year, and that's one reason why one year it's fairly good to watch the Perseids. The following year, it's 11 days different in cycle, and it's probably going to interfere. Now, this I find staggering. This is the modern value for the average new duration from new moon to new moon. The Babylonian value is less than a second difference. And this is 500 BC. It's 1 part in 5 million accuracy. I doubt if there's anything that was accurately measured back then. Just amazing. Now, here we have a path of the lunar cycles going around. And of course, it's not that the Earth stops here and then the moon goes around it and then it hops to there. It's just a continual thing. And the moon just waves a little bit. It doesn't ever go backwards. Now, if the moon were only affected by the Earth's gravity, what you would have is every year in August, i.e. this is cycle 0, you would have an eclipse towards Leo. And 6 months later, you would have an eclipse towards Capricorn. The only problem is the sun's gravity tugs the moon so it bends a little bit each time, and these angles are actually accurate. And it turns out that it bends a little bit, 19 degrees, and you get an eclipse season every 5.8 lunar cycles. A similar thing happens with the perigees and apogees. Last February, there was an annular eclipse over Argentina, and that means the moon was further away from the Earth than normal. And for August, it's going to be closer than normal, which gives us a total solar eclipse. Of course, my diagram is exaggerated. Counting the sun, you now get these things bent. Now, here's the amazing thing to me. 2,000 to 3,000 years ago, the Babylonians knew that. How did they know it? They had a systematic way of keeping track of astronomical events. And they were on cuneiform or clay records, and some of those have been lost, and some of them haven't been translated, but a number have been looked at. Now, what did these things record? The dates of events like comets, the first morning sighting of Sirius, and that's important because it makes sure the calendar keeps locked into the real cycle of the Earth. Planet locations, eclipses, but there's also a systematic record of the lunar positions. There are lunar 6 events, and the date and time of each is recorded. Now, this picture shows the first crescent moon, and that's Jupiter, by the way, by accident. I didn't realize it was there. There are 4 involving the full moon, and they're a little complicated, but the last moonrise before sunset is one of the events. So they recorded the date and time in each. They also recorded the lunar latitude. So these people knew the stars, and they could look at the moon, and they could see the stars, and they could say, this is a little above or a little below the normal position of the moon, and they could get the lunar latitude. One thing that amazed me, and actually I emailed somebody, is they didn't record the azimuth events. It would be very easy to have one observing place and to have markers like Stonehenge where this is north, etc., and they could have got an estimate of where these events happened, but they didn't do that. They used water clocks. I couldn't find a Babylonian water clock pictures, but they're not very accurate. The water viscosity doubles over 30 degrees C, but they got the times. They found patterns in the data. And one of the patterns is 18 years, 11 days, and 8 hours, and it was called a saros, that I gather means 360. I'm not quite sure how that happens. So the Babylonians could say eclipse season is usually 6 or 5 lunar cycles apart. But observers at one place cannot see all the eclipses. Sometimes they happen the other side of the Earth. Sometimes they're low magnitude where 10% of the sun is being blocked. That's hard to see. Sometimes, of course, you have lousy weather. A lunar eclipse, you can see about half of the Earth can see it, but a solar eclipse, maybe a quarter of the Earth can see part of it, and I worked out the length of the path times 100 kilometers, and it's about 0.3% of the Earth's surface, which is about 1 every 330 years to repeat, and I think it's a little more than that, but it's in the right ballpark. Now, here are the numbers of the moon's orbit, and you have 4 periods. The sidereal is compared to the stars when it goes past Leo again. The new duration is the longest. The node, that's where the nodes are turning, and it's a different number. And the perigee duration is a different number. Now, the saros explanation is that 223 new cycles is this number of days. A slightly large number of node cycles, remember how the sun turned the node slowly around, is almost the same time, only 52 minutes longer. And the perigee cycle is a little bit longer, but it's roughly the same. So that means if you have an eclipse and another one is going to happen this time later, and it's going to be roughly the same node position and the same position of being close to the sun or far away. So my only solar eclipse was about there in Turkey. It was really rough. We had to climb a 400-foot castle, and we saw the shadow of the moon descending the Tigris Valley. I don't think Nebraska will quite get the same thing, but hopefully not. Now, the next one is going to be this number of days plus a third of a day. And a third of the day, the Earth rotates to there. So my only other eclipse and this one are part of the same saros cycle. And another, that number of days, you're going to have a comparable eclipse with 2.5 odd minutes of totality over China. But wait a minute, 3 of those is going to be roughly a whole number. And it's only going to be 52 minutes short. And it turns out there was an eclipse in 1963 that was a little further north than this one. And the period of the 54-year, 34-day cycle is called, I don't know how you pronounce it, Eclipses. And Ralph, I think that was when you first got interested in astronomy, seeing that eclipse, right? And you're going to be one of a very small group of people, if it's clear in Salem, to see a second eclipse in the same Eclipses. And I don't know whether it's going to be 50 people, 1,000 people that have done that, but it's a pretty small number of people that have seen that. So, this is the Babylonians. They found the cycle of 5 or 6 lunar cycle patterns near the full and the new moon. They found the saros pattern, the 223. They found the 53-year cycle, not sure how much they used to predict, but they didn't make many mathematical models. So they have a rough idea there's going to be a lunar eclipse, not such a rough idea of a solar eclipse. So did those ancients predict eclipses? Maybe. Now we get to the Greeks. Alexander the Great conquered Babylon, so they got all the Babylonian records. They made mathematical models using geometry and trig, and they're 2 giants of Greek astronomy. Hipparchus lived 190 to 120 BCE. Is that okay? It's an acronym. Okay. And Ptolemy lived 300 years later after Christ. So Hipparchus's books have been almost all lost. Ptolemy referred to Hipparchus's books, and it's a question whether Ptolemy's ideas are his alone or whether he just copied Hipparchus. And years later, some Muslim scholars went to the emperor in Constantinople and said, can we copy this book? And they translated it into Arabic. All of the Greek versions of the book were lost. So it was translated to Arabic. So you have an interesting translation process. It went from Greek to 300-year later Greek, to Arabic, to Latin, and then to English. So it's interesting how these things spread around. Greeks worked under 2 assumptions. First is that the Earth is the center of everything, and everything revolves around us. So you have different spheres with the moon on it, the Venus, the sun, Mars, the distant stars, other planets, everything orbits around the Earth. The second one that makes less sense to me is you have uniform circular motion. So the sun moves, this time counterclockwise, because it's from the perspective of the Earth, it moves evenly compared to the center of movement. This was their assumption. But you can make an equatorial ring. This one's in Canberra. An equatorial ring, this points exactly to the celestial pole. This one points exactly where the celestial equator is. And on the equinox date, you have the sun being on one side, so you get a slight reflection here, there. Then you have just a complete shadow. Then you have the reflection on the other side. You can get the time of equinox to within a few hours of this. And solstice can be found by just the shadows and the shortest day. Oops, wrong button. So these are modern values for season lengths. And obviously, it can't be even circulation because the summer is longer than the northern winter. Solution? Then you have the Earth that is the center of everything, but the sun orbits somewhere or moves compared to a different spot than the Earth. And it turns out mathematically, knowing the number of days from each season, and these are the, wait a minute, this would be the solstice times and this would be the equinox times. You can work out where this sun is compared to the Earth as a percentage of the sun's orbit, and you can work out the angle between there and there. So I always thought these were just pretty diagrams, but they're more than that. 61 days after the equinox, the sun will have moved 61 divided by the number of days of the year, which is 60.12 degrees. You know that angle. We also know that angle from a previous calculation, and I just measured this in the diagram, but you can calculate how far the sun has moved compared to the spring equinox to where it is. You can predict where the sun's going to be at any given time. What about the moon? Moon's more complicated. It's tilted. And, oh, I forgot the sheet. This is part of the Almagest, and it's a diagram, and I still can't figure it out. This is the Earth. Something is moving at a constant rate around the Earth, connected to something that goes to this spot, and then the moon goes in a constant rate compared to that spot. And by working out where the sun or where the moon is at different times of the lunar cycle, you can work out the different values of those parameters, and using calculation, you can work out where the moon is going to be at any given spot. Now you're predicting locations. What's the accuracy of Ptolemy's model? About 1.5 degrees of longitude, which is 3 hours of the motion of the sun. Anybody heard of Christopher Columbus? His fourth mission, he traveled all around, and he suddenly found his boat was getting eaten away by worms, and he didn't think he was seaworthy, so he went into a bay in Jamaica and sent some sailors in a rowboat to Santo Domingo to get rescued. The governor was rather slow to rescue him, so he originally got food from the Arawak Indians, but eventually they said, we're not happy to feed you anymore, and it was a conflict. But the almanac, almanac that people used to navigate, said there's going to be a lunar eclipse on leap year day 1504. So he called the Indians to a meeting on that day, and it was the eclipse was actually supposed to start a little after sunset. The problem is when the Indians were there and the sun set, he realized that the moon was already being eclipsed. So it was wrong by a few hours. But he told them that I made the moon go away because the gods are angry because you're not feeding us and you have to feed us. And I'm going to go in the tent and talk to gods. And he went into a tent and he had an hourglass to time how long the eclipse was going to be. Then he came back out. This is according to his diary. He came back out, and the Indians, he said, if you promise to feed us, we'll make the moon come back. And of course, the moon came back, which is would have anyway. And but that illustrates the inaccuracy of this model. So, Ptolemaic astronomy, it was authority for about 1.5 millennia. And it was approximate predictions, but it was limited accuracy, especially for solar eclipses. So, did the Greeks predict eclipses? Maybe. Then came an amazing period of history called the Renaissance. Copernicus, planets move around the sun. Galileo, moons orbit Jupiter. Kepler, my hero, ditched the uniform circle idea. And David is symbol of an explosion of art. Michelangelo, Shakespeare, Leonardo, just an incredible era of history. Kepler, by using data that he stole from Tycho Brahe of Martian positions, was able to figure out that objects in orbit go in an ellipse, not a circle. And ellipses were well known at that time, and lots of people knew about them. His second law, in some way, is more important, because this showed this planet moving here would sweep a certain area in 30 days. And he was able to show that when it's closer, it's going to sweep the same area. And once they figured calculus to work these things out, you could predict where a planet is going to be at any spot of its orbit with much better accuracy than before. And of course, Newton, Euler, Halley, Meyer, Bessel, all sorts of people contributed things, and they figured out the three-body problem where you have these other effects. And only then did you get the first eclipse map. Now, if you have a November 2012 Sky and Tell, or if you can remember eclipsemaps.com, there's an amazing story in these maps. What this guy, Weigel, is the first guy to do it, and he predicted this eclipse on what's the 2nd of August, 1654. It's going to, the path of totality is going to go here, and that's the first time anybody predicted the path of totality, and he said the greatest eclipse would be in the Crimea. Now, what's needed to figure out exactly where an eclipse is going to be? You need to know the exact moment of the new moon so you can figure out where on the spinning Earth the greatest eclipse is going to be. You need to know the time between the new moon and the node crossing. Remember, it's going either up or down compared to north, and that tells you whether it's going to be an eclipse in the southern hemisphere or the northern hemisphere. And the other thing you need for this is accurate Earth maps. You could work out the longitude and latitude of where it's going to be, but look at how inaccurate the map of Africa is, right? So these things were a work in progress, and they got improved. Now, eclipse chasing. Lots of people to chase eclipses, including someone with a license, with that on his license plate. Let's say the richest person in the world, maybe the King of Spain, wanted to see this eclipse. So he gets a telephone call from Weigel. Oh, they weren't invented yet, that the eclipse is going to be in Crimea. Then he orders the Royal Air Force to fire up the Royal Jet, fly to Crimea International Airport, land, park at the best spot, and he would have missed totality because the mathematics wasn't there yet to be exact. So eclipse chasing is a recent phenomena, and that's where we have it. Now, there are all sorts of examples in literature, King Solomon's Mines, Connecticut Yankee, where people did what Columbus did and threatened, and it's easy to write that in a story. The logistics is these explorers, I think they're grave robbers actually is a better description. They would have to know exactly where they were on the Earth to be able to predict that, and I doubt if they had the navigation equipment. Okay, here's an eclipse map that we've all seen. I'm going to be in Nebraska with Dennis Gray and a whole bunch of other people. This is a close-up, and it shows this is the center line, but when you're 3/4 of the way to the outside, you still get 2 minutes instead of 2 minutes and 30 seconds, so you don't have to be right on the center line. Next picture shows a little town. We're going to be at the KOA here, but Minden. And I'm going to end with a picture of Minden. This is from Google Maps, and there's a house here, but I couldn't get the same picture by going further back. And let's say I'm driving near Minden and see the water tower here on the highest hill of town. And let's say I'm driving along here and I see some kids playing, so I roll down the window and I say, "Are you going to watch the eclipse on Monday?" "Oh yeah, we're looking forward to it." And let's say and then I ask them, "Well, where are you going to observe it from?" And they could say, "Oh, from my the yard." And I could tell them, you know what? The difference between an almost eclipse and a complete eclipse is staggering. And if you go to the parking lot there, you can see a total eclipse. You probably won't see it from here. And that says something about the state of modern astronomical understanding that I find terribly profound. It's a result of 3,000 years of observations, math, discoveries, and I take my hat off to the people that have done that. Thank you very much, and I'd love to have some questions if you have any. Oh, should I have called it how the ancients predicted eclipses? Or should I have called it how the ancients didn't predict eclipses? Because, what's that?
Almost.
Yeah. They weren't bad on lunar eclipses. Anyway, are there any questions? I threw a lot at you, but it's really fascinating. Yes?
What about other cultures like the Mayans or Chinese?
Okay. The Mayans, they had a major library where they kept all their astronomical records, and some Spanish general came there with soldiers, put everything outside, and burned all the records. There are a few that were kept, and I can go forward here to it. Oops, there. There is one record that was taken before this fire happened, and it has the number 223 in it, which means they figured out the saros pattern from thousands of years of observations. Chinese, I'm not aware that they worked out the elliptical path of the orbits, which is key to working out where the moon's going to be at a given time. But there were major treatments of eclipses there as well. I actually got a whole bunch of material on Chinese eclipses, but I didn't get a chance to read it because I was focusing on the rest. There's only so much I could include, but there were discoveries. But to me, the key is what Kepler did. You know, elliptical patterns, it explains the orbits and everything. Okay. Was there another question up there? Yeah.
India.
What's that?
They keep records.
Yeah.
Oh, all right. He mentioned those two cultures. The Almagest that Ptolemy wrote, maybe I should stay here. The Almagest that Ptolemy wrote was translated into Arabic. It was also used by Indian astronomers. I don't know if they translated it to Sanskrit or whatever the dominant language would have been then. There were all sorts of advancements of slightly better epicycles and everything else. But again, I haven't read anything that indicates they figured out orbits are ellipses and everything that is really needed to predict solar eclipses. Lunar eclipses, they could predict fairly well, but solar eclipses, to say there's going to be an eclipse on this day at this place, my reading says not. But again, I didn't, I only had so long to talk, so I didn't go into that in the depth.
This continental Indians, not
What's that?
we're talking about, I think the gentleman was asking you about subcontinent India rather than Indians in America.
No. I was thinking of the Almagest. I don't think the Almagest was sent to North America. You know, like I was thinking that it traveled from Islamic countries through to India and was used by astronomers there. Yeah, that's what I was referring to. Is there another? Okay. Anyway, thank you very much.